Good morning, students. Welcome back to our physics classes. Welcome to the new session of our revision classes. Today we are going to revise the chapter Kinetic Theory of Gases, Behavior of Perfect Gas and Kinetic Theory of Gases. So we have already seen the concepts which are described in this chapter, and this chapter describes the behavior of a perfect gas. And this chapter starts with the concept of a perfect gas, ideal gas. So, an ideal gas can be a gas which obeys the ideal gas equation, PV is equal to mu RT, where P pressure, V volume, T temperature, R is the gas constant, and mu is the number of moles there. So, equation of a state for an ideal gas, it is given by. Actually, it is given by ideal gas equation PV is equal to mu RT. Actually, it is the combination of the two gas laws, Charles law and Boyle's law. You are knowing what is Boyle's law. Boyle's law says that constant temperature, volume is inversely proportional to the pressure. At constant temperature, volume is inversely proportional to pressure. And Charles law says that at constant pressure, volume and temperature are directly proportional. Volume and temperature are directly proportional at constant pressure. These are the Charles law and Boyle's law. So from Charles law and Boyle's law, we are deriving the ideal gas equation that we have already seen. From Boyle's law, at constant temperature, P proportional to 1 by V, and at constant pressure P proportional to V. So V proportional to P by P. So PV is equal to RT. This case of a 1 mole of gas, if it is n mu moles of gas, mu RT. This we have already seen this derivation, or how we can get the ideal gas equation. And number of particles in 1 mole, it is given by 6.023 into 10 to the power 23 particles are there in 1 mole of a gas, and R, the value 8.31 joule per mole per Kelvin. 8.31 joule per mole per Kelvin is the value of universal gas constant R. So any gas that can be described with the ideal gas equation is a perfect gas. And a gaseous system, generally when we are talking about a gaseous system, the particles are in random motion, and there is no intermolecular force or interparticle force between the particles in a gaseous system. All these matters are there that we are knowing. But kinetic theory of gas describes the gaseous system perfectly. Kinetic theory of gas describes the gaseous system perfectly. So for that, different postulates are given. Any gaseous system contains tiny identical particles called molecules, and these particles are in random motion. There is very less attractive force between them. So during their random motion, they collide with each other, and they collide with the walls of the container in which it is taken, and they can impart pressure on the walls of the container, and the collisions are perfectly elastic. And time duration between two successive collisions is the relaxation time, and the distance traveled between two successive collisions is known as mean free path. And the molecules are moving with a particular velocity called RMS velocity. We will come to that. What is RMS velocity? Anyhow, they are moving with the velocity RMS velocity. And from this we are interested in that point of exerting pressure. That means pressure is exerted by a gas on the walls of the container in which it is taken. So we have calculated that pressure exerted by gas on the walls of the container, and that pressure is proved to be P is equal to 1 by 3 rho V square, and this is the RMS velocity. And actually it is 1 by 3 into M by V into V square. See, M by V is the mass per volume. So that will become 1 by 3 into N into M divided by V into V average square. So this N is the total number of particles there, and M is the mass. So if there are n moles of particles, mu moles of particle, if there are mu moles of particle and in 1 mole n number of particles are there. In 1 mole n total number of particles are there. If there are mu moles, then mu n number of particles will be there. Okay. So this n you can replace by n is equal to mu into n. So that will become 1 by 3 into mu n m divided by v into dr square. So what is n into m? M is the mass of one particle and n is the total number of particles in 1 mole. So that is n into m can be replaced by molecular mass. So 1 by 3 m by v into v square. So that is the equation for the pressure exerted. For that we were considering a gas particle. Initially we are considering a gas particle which is moving from left to right. It collides with the and we have chosen a cubic container there. Within the cubic container a gas is taken and from one side the gas molecule is moving towards the right hit with the opposite phase and it is bouncing back. Then 2L is the total distance travelled with a velocity v. Then the distance travelled and all these matters you are remembering all these matters. That means we have calculated the time taken for okay, we can find out the momentum change occur when a particle makes a collision with one phase, then that is 2mvx and the distance travelled is 2l and the velocity is v. So v by 2l, velocity by distance by velocity is the time taken. When you are taking its reciprocal, you can take the number of collisions. So when one collision 2mvx is the momentum imparted multiplied by the number of collisions, then after that you can calculate the force. Force is momentum imparted per unit time. So that is force, then force per area will be the pressure. Then you are considering only one particle there, then you have to consider all the particles are moving along the same direction, that means in the x direction, and moreover it has an equal probability of moving along x, y, z direction. So vx square we can take it as 1 by 3 v square average. Then finally we are getting that equation 1 by 3 rho v square. That is a pattern of deriving that equation. And from there we have defined the root mean square velocity. What is RMS velocity? Root mean square velocity. Why we are choosing RMS velocity is very important term, RMS velocity. So what is RMS velocity and how or why we are taking RMS velocity? We know particles are in random motion. So when you are adding the velocities of each particle, that may be result in 0 because all the particles are in random motion. So avoid that. That doesn't mean that the particles are at rest. They are moving. So to avoid that, what we can say, avoid that discrepancy, we can square all the velocities. So the negative velocities are also become positive. Then you can take the mean and take the square root to get the average velocity of one particle. That is the RMS velocity, root mean square velocity, root of mean of squares of individual velocities. Okay, so that is RMS velocity. So from RMS velocity or the pressure equation, we can have the thermal equilibrium and kinetic interpretation of temperature. Kinetic interpretation of temperature means how temperature is related to the RMS velocity, because kinetic interpretation means we are already said that is the average kinetic energy of particles present in the system temperature. So it is related to its velocity. So how RMS velocity is related to temperature, or what is the relation between RMS velocity and temperature? That is the kinetic interpretation of temperature, which means as the temperature increases, VRMS also increases, and we are getting that VRMS is proportional to root of temperature, absolute temperature, square root of absolute temperature. So that is the kinetic interpretation of temperature. Then we can have the relation between root mean square and molecular weight. Root mean square and molecular weight. And it is proved that root mean square velocity, VRMS, and the molecular weight are inversely proportional. Again, a square root. VRMS inversely proportional to square root of molecular weight. Then relation between kinetic energy, relation between temperature and molecular kinetic energy. So kinetic energy is given by 3 by 2 kT. 3 by 2 kT. Average kinetic energy. Average kinetic energy of a molecule is given by 3 by 2 kT. And energy of particles is 3 by 2 RT. Kinetic energy of a gaseous system is given by 3 by 2 RT. There you are having that relation. Our kinetic energy will be 3 by 2 RT. 1 mole of gas is 3 by 2 RT. Kinetic energy of 1 mole of gas is 3 by 2 RT. And when you are calculating the average kinetic energy, then it will be 3 by 2 RT divided by N, where N is the total number of particles in 1 mole. So what is R by N? R by N is another constant which is called as Boltzmann constant. So that will become 3 by 2 kT, where K is the Boltzmann constant. Boltzmann constant. Okay, R by N is Boltzmann constant. So you can calculate the value of Boltzmann constant. Its value is 1.38 into 10 to the power minus 23. K is equal to 1.38 into 10 to the power minus 23. Okay, so that is Boltzmann constant. That is the relation between average kinetic energy and temperature. Temperature and average kinetic energy. Then another term that we have described here is degree of freedom. Degree of freedom means the possible ways of movement of a particle or possible ways of energy distribution by a particle. So when you are considering a single particle, it has 3 degrees of freedom because it has an equal probability of moving, x direction, y direction or z direction. So 3 degrees of freedom having a monoatomic gas. If it is a diatomic gas, then it has 5 degrees of freedom. 3 translatory and 2 rotatory. And if a polyatomic, it is 6 degrees of freedom. Okay, so a degree of freedom, using degree of freedom, you can define the value of gamma. Gamma is Cp by Cv. And Cp and Cv, you can have Cp equal to Cv plus R. So from these, you can calculate the value of gamma. Okay, so that is degree of freedom, and from degree of freedom you can calculate gamma. So if in a question, if gamma is not given, if it is a diatomic molecule or triatomic molecule is given, then you can easily calculate the value of gamma, because if you are knowing the value of degree of freedom for a particular system, you can have Cv is equal to 1 by 2 Fr. Cv is equal to 1 by 2 Fr, where it is the number of degree of freedom, and Cp you are knowing Cv plus R. So gamma is equal to Cp by Cv. You can easily calculate the value of gamma. If it is not given in the question, they can easily calculate gamma and make use that. Okay. So then another term that we have used, that we have found in this chapter is total internal energy of a gas, ideal gas. So that is 1 by 2 FKT. And we have said that 3 by 2 kT is the kinetic energy, and this is 1 by 2 into FKT, that is equally distributed along 3 degrees of total kinetic energy of a system, or average kinetic energy of a system. System means gaseous system. A gas is equally distributed along 3 degrees, all the degrees of freedom. If it is 1 by 2 kT, it is a single molecule, monoatomic gas. So degrees of freedom is 3. That can be 1 by 2 kT multiplied by 3, where 3 is the degree of freedom. So we can say that 1 by 2 FKT. Generally, it is 1 by 2 FKT. Along each F, 1 by 2 kT is distributed. That is equipartition theorem. That is known as the equipartition. The average kinetic energy of a gaseous system is equally distributed along the each degree of freedom. So average kinetic energy is given by 1 by 2 FKT. That is equipartition theorem. Okay. Then mean free path we have already defined, and we got the equation as lambda is equal to kT divided by root 2 pi d square rho, means pi d square p. So that is the mean free path. That is the mean free. Then the final point that we have seen is the Avogadro number and its significance. So Avogadro number is already familiar to you. That is the total number of particles present in 1 mole of gas. Okay, so these are the topics, and here we have to focus more on the gas laws, then gas pressure, then the results that we have derived from that, that is kinetic interpretation, then relation between VRMS and molecular mass, kinetic energy, average kinetic energy, degree of freedom, equipartition theorem, then gamma. Okay, so these are the content from this chapter. I suppose already you have revised this chapter. Then, keeping all these points in your mind, once again you revise it and keep the concepts clear with you. Okay, already you got the numericals from this chapter, so similar problems you can find in the textbook that you can solve. Okay, for the next class we will meet with another chapter. So till then, bye.